Okay, hi everyone. I'm filming this from Washington, D.C. It's actually snowing outside. So it says in my slides Tuesday, January 29th, and actually it is Tuesday, January 29th. Although the hotel internet is so slow, I'm not sure when I'll get these uploaded, but I'll do my best. So I'm going to break this into parts, and so this is the first part out of maybe four, but as I go, I may decide to break at different points. So here we go. You're not seeing me this time. This is the second lecture on transforms. So we did one on Thursday that was just to kind of get us ready for kind of the linear algebra behind transforms. And so this is the one that actually has the math that you'll need to do Project 1E. So first, just some announcements. This is our regular office hour schedule, and it's actually all normal this week. I guess Roscoe's Monday and Tuesday office hours have already passed. If I'm able to get this posted Tuesday night, then you can go to his Wednesday office hours. I will have office hours after lecture on Thursday and again on Friday. Here's the timeline. So we've been following the Citro. I think I put this up last Tuesday, and so now we're a week ahead. I'm in DC. You're all working on 1D, and it's due on Thursday. I will assign 1E on Thursday. It'll be due in 1 week. 1E involves some math, and so probably we'll have a bonus office hour before the Super Bowl on Sunday. It might be in the morning. I'm still kind of deciding when it will work for me. But I will we'll discuss it on Thursday. Okay, so here's our goal. There's 5 different spaces, and so I'm going to quickly describe the spaces. And what we want is we want to take triangles, which are in world space, and we talked about world space in Thursday's class, how we would specify a triangle with 3 coordinates. They'd be 3-dimensional coordinates. Recall on Thursday I used the back left of the classroom on the floor as an origin, and then we talked about how to describe the chalkboard in terms of the basis vectors in x, y, and z. And so all of our models have 3 vertices with 3 x, y, z components, which are all relative to some origin. And so our goal is to get to the space that you've been rendering in, where your triangles overlap with the pixels. And we're going to have to go through some intermediate spaces to get there. And so the first space will be called the camera space. And with camera space, the camera is located at the origin, and it's looking down the minus z axis. And the triangles are transformed to be relative to this camera. It has its own frame. The next space is the image space. And with the image space, all the viewable objects go from in x and y and z from -1 to +1. The next space is screen space, where you project away z and you go to just the xy plane. And the last space is device space, where all the triangles have overlap with the pixels. Now, we're actually working kind of a funny space that is device space with a z buffer. So we actually don't throw away the z as we go from image space to screen space. And even though what I have here on this slide is conceptually, what we're doing, we're going to keep the z's all the way to the very end, and I'll talk more about that. In fact, I'm going to spend the next few slides talking about each space and then the transforms that take them between us. So the first space is world space, and so world space is defined by the user's coordinate system. So when you set up the triangles, you decide what the origin is, and then you decide where all the vertices go. And it says the space, I'm just going to read this, contains the portion of the scene that is transformed into the image space by the camera transform. So that sentence tells us what's happening next. We're going to take our triangles and we're going to apply a transform to them called the camera transform, and that's going to take us into, and it says image space, I think it takes us to camera space. And actually I think that's called the view transform. So this is not a good start to this lecture, but I'm going to keep it rolling. We'll see in the future slides that many of these spaces have bounds, world space, bounds like I had said, in image space it goes from -1 to 1. In world space, one option is there's no bounds, and the other option say, well, I declare that the vertices should never go outside this range. But bounds are kind of less meaningful in world space. So good. So indeed, my slides are very wrong because the transform from world space takes us to camera space, and it's called the camera transform. So so the camera transform was right, but it's transforming us into camera space, not image space. So when I upload the slides, I'll upload the correct version. And so this will be one of the YouTube videos, is specifically how to make the camera transform. Okay, camera space. This is the space where we're looking down the z-axis, and again the camera is at the origin. And in this space, it has its own frame, and we talked about frames before. Frames are basis vectors with a coordinate, an origin. And so the origin is where the camera is, and the frame has 3 vectors, and one of them is looking down the minus z-axis. And so we would be taking triangles, and we'd be applying this camera transform to get the triangles so that they're positioned here, at least the visible triangles, so that we're closer to having it be that the triangles overlap with the pixels on the screen. So here's how camera space works. The idea is that we've got some camera C, and we've got some focal point. Here in this picture, it's A, and then some view angle. So if this angle alpha is very wide, we'd have a fish angle lens. If it was very narrow, we'd have the opposite of that. Now, there's something that's used in computer graphics, which is not immediately intuitive, which is there is a notion of the nearest thing you can see. And in fact, if you put your finger very, very close to your eye, you're no longer able to see it anymore. And so this near plane, everything closer to the camera of the near plane is invisible. And the far plane is the same idea, that everything further away than the far plane is also invisible. So the only things that are actually visible are between the near plane and the far plane. Now this picture is a little misleading because it makes you think the near plane and the far plane aren't very far apart, and we're looking at a kind of thin band of triangles. Typically the near plane is going to be very close to the camera, and the far plane will be very, very far away from the camera, and the visible region is quite large. In this case, it's quite small. So if you take a solid, like a cone, or in this case a pyramid, and you truncate it, you cut it, so you cut off the tip of the pyramid, and you only have the base that remains, that's called a frustum. And so you'll often hear this visible region here referred to as the view frustum, and I will use that term today and throughout the rest of the course. So here are the data members that go along with the camera, and these are exactly the data members that are in my project. There's a near and a far plane, and this is just distance from the camera to the near plane if you go through the middle, right? So if you go if you go off axis, if you follow this edge up here, the distance is longer, but the near plane actually describes the distance to the closest point on this plane, and the far plane, the far data member, describes the distance from the camera to the closest point on the far plane. The position is the position of the camera, and the focus is the focal point, A, right there. And then up is something I'll describe in a few slides. Okay, so once you have things in camera space, then you convert them to image space. And as you can see, this is a little bit unusual that we've got here this view frustum, where we have a smaller frustum in the front and a larger one in the back. And when we take it through the view transform, we're actually going to turn this into a perfect cube. And what that's going to do is it's going to make things that are in the front get larger, and things that are in the back get smaller, at least relative to the things in the front. And so that creates the perspective that we're used to seeing in our everyday lives. Okay, so about the image space. Image space, again, 3-dimensional coordinate space. It's the output of the camera transformation. Output of the view transform. Wow, these slides need to be updated. Output of the view transform. And the bounds go from -1 to 1 in x, y, and z, or sometimes from -1 to 0, which is what we did in Project 1D. And it just depends on how you define your space. Okay, so here's this notion of up, coming back to up, and so there's an up vector, and so this is now showing us the bounds of the image space, what is being transformed into image space. So this right plane, if this is up, and I guess this is too bad that I haven't really described up yet, but up is a vector, and let me just scoot ahead, hold on. This is a slide fail. I'm almost there, I think. Okay, so up is the direction from the base of your nose to your forehead. So the camera, if you're a Cyclops, the camera is on one of your eyes, and then up is the orientation that you're used to seeing in your brain as up. And so if you're sitting on your couch and this is what's playing on the TV screen, then this is what you'll see. You'll see the picture you expect. But if you're lying down on the couch and you look at the TV screen, then the picture is rotated 90 degrees from if you were sitting on the couch. And so the up axis just shows you the orientation of which triangles should be on the top of the screen and which triangles should be on the bottom of the screen. So now let me go back. And so here is our up vector. Remember, that was part of our camera description that I didn't want to discuss at the time. Here's the up vector. And so this just says which direction is up going. And if this is the direction that we're looking at, the direction we're looking at is A, the focus, minus C, the position. If this is the direction we're looking at, then the up vector will typically be perpendicular to it. It'll be at a 90-degree angle. Or at least that's a desirable property. And we'll talk more about that in a little bit. So the idea then is if we're looking at camera space, our view frustum, and trying to see where it will go in image space, then it works like this, that the x equals 1 plane of image space will be this right side of the frustum, and the x equals minus 1 will be the left side of the frustum. Y equals 1 will be the top of the frustum, and y equals minus 1 will be the bottom of the frustum. And then z equals 1 will be the front of the frustum, and z equals minus 1 will be the back of the frustum. And again, this fits the convention that we've been doing in Project 1D, where things with bigger z values are in front of things with smaller z values. So here's z equals minus 1. At the far plane, the furthest thing we can see, and z equals plus 1 is on the near plane, the closest thing we can see. So things that are on the near plane should go in front of things that are at the far plane. Okay, the next is the screen space. And so this is projecting what we have in image space onto the plane z equals 0. And if we have a point 0, 0, z in image space, then that will go to the center of the display screen. It would be 0, 0 would be the very middle, because this would be x equals minus 1, this would be x equals plus 1, y equals minus 1, and y equals plus 1. So if we have 0, 0, that's the middle, and any 0, 0, z will project to the center. Aha, and there's my diagram, x minus 1 plus 1, y minus 1 plus 1. Sorry, I actually, when I present it this way, I don't have my presenter view so I can see the next slide, so which is helpful to know what the next slide is. So apologies that my slides aren't perfectly rehearsed here. The last space is device space, and so that's the space you're most familiar with. With device space, you go, instead of from minus 1 to 1, you go from 0 to the width of the image, or the number of pixels in width, and from y equals minus 1 to plus 1, instead from 0 to the height of the image, or the number of rows in height. So this is the lowest level coordinate system. It's the closest to the hardware coordinates of the device itself. It's defined to be an n by m array of pixels. We're very familiar with this at this point. And the coordinate system is imposed on the space. The lower left-hand corner of the array is 0, 0. So the origin is set by this space. And so then here's an example where we've got pixel 0, 0 on the left and pixel 15, 15 on the right. And here's 1, 2, 3 over and 7 up, and that's pixel 3, 7. Again, this would mean column 3, row 7. Of course, there's a temptation to write this as 7, 3 as well, because we often say row before column in English. And of course, as I already mentioned, we're in this weird space where we're doing device space with depth information. And so this is now doing where the coordinates are from 0 to n, where n is the width, and 0 to m, where m is the height. But now we have a z, and the z again it's going to go from -1 to +1 or -1 to 0. So I think I'm going to stop here, even though there was a couple errors in this video, because I think it's enough, but I will correct the slides as I upload them. So here's me, and I'm going to stop the video, and we'll do an experiment to see if the hotel Wi-Fi is fast enough to upload some of these. Bye, everyone.